Hello, we are Brianne and Luke, and we are finding diabetes in the community. So diabetes is when blood sugar is high, usually not to responding to insulin or not making enough insulin. Prediabetes is essentially high blood sugar, but it's not high enough to be diabetes. Prediabetes often is a stepping stone towards diabetes, but it is reversible if lifestyle changes are made. They share the same risk factors, so age, obesity, physical inactivity, and a poor diet put you at greater risk for developing diabetes or prediabetes. And both of these conditions share similar consequences and long-term effects beyond just high blood sugar. These include damage to blood vessels, so like a stroke or a heart attack, as well as damage to nerves and eyes, kidneys, and gums. As you can probably guess, these are pretty expensive and can lead to a decrease in health quality, as in quality of life, and potentially it could lead to death. According to the CDC, diabetics are about 11% of the population, while prediabetics are 38%. And since prediabetes can go to diabetes, that's potentially almost 50% of the population is experiencing these long-term damaging effects. Our goal is to develop, train, and test multiple models to find the best one at predicting diabetes with reasonable recall and precision, so it won't predict it when it's not there. In addition to using precision and recall, we'll use the F1 score, which is the harmonic mean between the two, but we will also consider how well the models predict given the imbalance in the proportions of diabetes and prediabetes compared to no diabetes. So why do we want to do this? Well, as we mentioned, early detection especially for pre-diabetic individuals is key to them making or having the chance to make better health choices to prevent themselves from developing diabetes. In addition to all the effects that we discussed, according to the American Medical Association, diabetes is the 7th leading cause of death in the United States. And in order to be able to find this without going out and doing a whole bunch of lab work on the community, we need to be able to predict it using less invasive means. So the data set we are using was taken from Kaggle, but it was provided by the CDC's Behavioral Risk Factor Surveillance System telephone survey. We focused on the 2015 data, although this is an annual survey. And this data has 254,000 entries under 21 predictors and one response, which is whether you have diabetes, you have prediabetes, or there's no diabetes. When looking at the predictors, there are 14 binary types where it's focused on health habits, like if you eat fruit and vegetables once a day, if you're physically active, if you smoke a lot, or if you are a heavy alcohol drinker. They also focus on general health history, like presence of high blood pressure or high cholesterol, or history of heart disease or heart attack. There are also 4 categorical predictors, which include the age group, because they just kind of grouped everything together. Every 10 years would be a new group, as well as the education level, your income group, and your general health rating. There were also 3 numeric types, one of them being the body mass index, or BMI, as well as just a report of the respondents' count of number of days in the last month that they had poor mental health or poor physical health. So focusing in on the for mental health or poor physical health, as well as the BMI. As you can see on our distribution graphs, that those have high amounts of outliers. They also have the largest range of values, with BMI going up to 100, and the mental and physical health bad days can go up to a value of 30. So what we did first is just remove all the outliers that were significantly impacting the data, based on which we use the quartile outlier removal equations. We would also scale the data in almost all of our models, except for the random forest model, since that does not need to be scaled. Because as you can probably guess, if we did not scale it, our BMI predictor especially would cause an imbalance in predictions, because everything would be more heavily weighted than the others. So the last thing we did with looking at the predictors was to go ahead and check for high correlations and just see how the individual predictors correlate with each other, as well as with the response of diabetes. And from what we found, there weren't any actual strong correlators, either positive or negative, but the highest one we did have was between education and income at a value of 0.44. And I'm now going to turn it over to Luke to describe the models we made, the conclusions that we formed, and how we want to move forward.
Thank you, Brianne. My name is Luca Wino, and I'm going to be talking about the modeling. Now, as Brianne mentioned earlier, we're dealing with 3 different classes that we want to predict. The class 0 is the class with no diabetes, class 1 is the pre-diabetic class, and class 2 is the diabetic class. Now, the orange line is going to be what was actually in the data set, and then the blue line is what the model actually predicted. So for this data set, we built 6 different models. So for the first model was a linear support vector machine model, and as you can see, it gave a false negative by indicating that there were less individuals that did have diabetes than was actually in the data set. And then it said there was no individuals with diabetes, and then over here it gave several false positives by saying there were more people that were non-diabetic than were actually in the data set. So this is a worst case scenario. In real life, we would rather have a false positive, label somebody as having diabetes, and then they go get a second opinion, get checked up, start treatment, start putting preventative measures in place, and then come to find out that they don't have diabetes, than tell somebody they don't have diabetes, they continue living their life when in reality they have diabetes and they don't make any changes, they don't put anything in place, they don't start seeking treatment, and it gets worse. For our second model was a logistic regression model, and it performed similar to the linear support vector machine. It predicted very few people as being diabetic, no pre-diabetic, and then it over predicted that individuals are non-diabetic. For our third model was a gradient boosted model. Now this one performed slightly better than the other models by indicating that there were slightly more people were diabetic, and it didn't over indicate as many more people as being non-diabetic. Now for this model, we also got the feature importance scores, and as we can see, for this model, it valued high blood pressure, generational health, BMI, and age as being important features for predicting whether or not a person has high chances for being diabetic. For the random forest, we built 3 different models. The first model was a trimmed random forest model, which was scaled, the outliers was removed. For our second random forest model was a random forest model just on the unscaled raw data. And then our third random forest model was a random forest model on a model where the target class was balanced. And For the trimmed random forest model and the raw random forest model, they had similar outcomes. They actually predicted, all their predictions were zero, where everybody in the data set was labeled as being non-diabetic. There were no diabetic or pre-diabetic individuals. Now, for our last model was a balanced random forest model. So for this model, of all the 6 models, it actually over predicted individuals as being diabetic, over predicted individuals as being pre-diabetic, and under predicted individuals as not being diabetic. Now, the blue line in this instance, as you can see, is higher than the orange lines. And then some of the important features that it took into making this decision: BMI, age, income, generational health, education. So it used more features to come to the conclusion to make the determination whether or not to label an individual as being at risk for being pre-diabetic or having diabetes. Now, we used, we initially considered precision recall as metrics to go for, and we went with F1 score, which is a harmonic mean of precision and recall. So we went with F1 score just for the ground truth, looking at actual correct values versus what's in the actual data. And the highest model that had the highest F1 score was a gradient boosted model. However, we were more focused on a model that could actually learn something from the data and do something with it. So our best model going forward, the model we chose was a balanced random forest model, which was had the lowest score, but it gave us better results by actually learning features in the data and making some predictions. Now, going forward, the next steps is to focus more on balancing the classes, try a few different methods to balance the classes, and then select the features and focus on which features, are correlated with diabetes. Prevention is key. Diabetes is the 7th leading killer in the United States, and more people live with it or are at a risk of having diabetes than not, and they don't know. So we need to be able to predict and let these people be aware. Once people are aware, then the choice is in their hands. So prevention is key, and thank you for your time.